Hi all, this is your Snow Day video lecture. Before you watch this video, you should have read the chapter. It's chapter 30 of your textbook. And for those of you that are in the habit of doing the online quizzes, you should have already done the online quiz for this one. And I would suggest to use this each time I move on to a new question. After the question becomes visible on the screen, you should pause the video and select your own answer to the question, and then move on to see the explanation. I think you get the most out of it if you do it that way. Alright, so here's the first one. Pause the video, answer the question yourself, and then move on. We're seeing the second derivative of y with respect to the position is equal to a constant times the second derivative with respect to time. This is a wave equation. Let's see. That one is definitely good. So A is good. It's a differential equation. I wouldn't call it an algebraic equation. It is a partial differential equation. When we take the derivative of y with respect to x, we keep t constant. That's why you get this curly d rather than the regular d. The curly d means the partial derivative. And also when you take the derivative of y with respect to time, you keep the x constant. So it is a partial differential equation. So A and C are cool. So I would say the best answer to that one is F. Alright, let's move on to the next one. What does the y stand for? This is a wave equation. The y represents displacement from equilibrium. So let's see if they got something like that. Nope, that's no good. Displacement from equilibrium is good. Period is nonsense. Wavelength, nonsense. Time, that's t. Wave speed, no. Velocity of n, it's got a typo in it. Velocity of an infinitesimal bit of the medium, no. And H, none of the above. Looks like B is the only one that makes any sense. The displacement from the equilibrium. It appears two places. When we're taking the derivative of it with respect to x and the derivative of it with respect to t. Okay, let's move on to the next one. What does the x stand for? This is where you're at along the length of a medium. So we got a wave and a string, and we can make a graph of y versus x, for instance, and x is how far you are along the length of the string from some end point. So position along the length of the medium. Yeah, this is more generic than a wave and a string as I was thinking of it, but certainly applies. Displacement from equilibrium, no. All these are nonsense. So yeah, A is the only one that comes close to being a correct answer, and it's perfect. Okay, let's take a look at this one. What does the V stand for? The V in this equation, you more or less have to know, is the velocity of the wave pattern. So the velocity of the wave itself. There are two velocities in this kind of situation. Like any given particle, you can say an infinite set of velocities is moving up and down, and so a particle in the medium has some speed which is continually changing. By the way, this v is a constant, the wave speed. So let's see, position, displacement, it's all nonsense. Period, wavelength, time, wave speed is in there, and the only other one that is kind of even the right kind of thing, in other words, it is a velocity, would be this, but no, that's exact, of the two possibilities, that's the one that it's not. This v represents the speed of the wave, not the speed of a particle of the medium. So that would have to be an F. Alright, moving on. Which way is the wave traveling? Alright, we want to look at this expression and say, if we're looking at a particular part of the wave, say a crest of the wave, for instance. So I'll draw a wave. Imagine that we're looking at a wave that's moving either left to right or right to left. So I just want to think of this as a snapshot of it, but it could also be a graph of y versus x. And if we focus our attention just on like this particular point right here, that corresponds to a maximum. So y is equal to y max. That means the cosine of this whole phase is 1, and so the phase is going to be 0 or some integer multiple of 2 pi for that to be the case. If you think of the way the cosine of theta looks as a function of theta. So I can think of this whole phase as the theta when I'm talking that way. Alright, so I could have done it with another point, this one, then I was the cosine had to be something else, but the point is that the phase has, if I'm focusing all my attention on one point, and I keep on focusing my attention on it, for that one point, the phase is constant. In other words, for that one point, even as I watch it moving over, the y is equal to y max. I picked a point that corresponds to a crest, and therefore this thing doesn't change. So I got to ask myself, all right, if t is increasing, and by the way, I'm considering the positive x direction to be the right. If t is increasing, but the whole argument of the cosine is not changing, then x must be increasing, so that the difference between these two terms never changes. If x were decreasing as t increase, increase in t causes a decrease in the whole thing because of the minus sign, and if x is decreasing, so becoming more negative, then that's a negative change in this term too, so we would have a change in the whole argument. The only way for this argument to stay the same, in other words, for this difference to stay the same, is that if one of the terms increases because the time is increasing, the other one has to increase as well. So if x is increasing as time increases, that means the wave is moving to the right in my picture, so it's moving in the plus x direction. Notice, had there been a plus sign here, then in order for this to stay the same, if t is increasing, x would have to be decreasing, and it would be in the minus x direction. So it's all about the algebraic sign in between the two terms. Alright, so it takes care of that one. Let's see if there are any more here. Yeah, I got a couple more. So this is, okay, I hope you paused, thought about it. This is just a memorization thing, a fact. We find experimentally that on reflection from a fixed end, say a crest going in comes back upon reflection as a trough. We get phase reversal when we're talking about a fixed end. We get no phase reversal upon reflection from a free end, but this question was about a fixed end. So we're thinking about a piece of string fixed connected to a wall, for instance, and at that fixed connection you do get phase reversal. Alright, next one. Alright, we got situation, one string, two waves. I'll just have wave pulses, one traveling that way, one traveling that way. I arbitrarily set them up so one's corresponds to displacement of points on the string downward, the other upward. When they get to the same point, we say what's going on is interference. The two waves are interfering with each other. That would be a reasonable name for it, but it's not what it's called. The jargon is interference. just B's the only option on that. Okay, what causes standing waves? I can think of two ways of answering this one. Standing waves are waves. What causes waves is something oscillating. So if I want to cause a wave in a rubber tube that I've got stretched across the classroom, I got to make my hand oscillate up and down to cause the waves. Standing waves are waves, something oscillating. If I wanted to get into the question of what makes it so that standing waves are persisting in some string segment, what's going on is that the original traveling wave, that wave that is resulting from the oscillations and traveling away from the point, from the oscillator. So if it's my hand going up and down, my hand is the oscillator. Those waves are interfering with reflected waves. So there's an end where somebody's causing waves. There's another end, and the wave that the person causing bounces back and forth from one end to the other, and the waves are interfering with each other. And if the frequency and the length of the segment, in the case of a string segment, are correct, then you get some. At some points, you always get constructive interference, and at other points, you always get destructive interference, and that's how you get a standing wave out of the deal. So, I would accept if somebody said something oscillating, I would have to accept that as a correct answer. Standing waves are waves; something oscillating causes them. But you have to be ready for a deeper question about it. Since this is just a discussion question, you have to be ready for the deeper question. What makes it so that standing waves persist, for instance, in a wave medium? And it's all about interference. It's about constructive interference always occurring at a particular point or points, and destructive interference always occurring at some other point or set of points. All right. So that does it for your snow day video lecture.